I apologize for the poor sound quality that we may have. I'm trying to get a video to play in the midst of this, and that may be the only way. So we're talking about superconductivity, but let's consider normal resistance, that an electron trying to pass through the crystalline lattice will bump into the nuclei along the way, and this causes the nuclei to increase their vibration. That's what we speak of as heating that occurs as a result of electrons trying to move through. But we also know that as you lower the temperature, the resistance in the wire goes down. That evidently this tendency of electrons to bump into these nuclei goes down as the temperature of the wire goes down. That perhaps because the crystalline lattice is vibrating, that causes it to get in the way, or at least come into the proximity of the electrons. And when the crystalline lattice vibrates less, then there is less interaction with the electrons and you get lower resistance. But this is not superconductivity. Otherwise, you would end up with some resistance when you got down to 0K. And superconductivity is a matter of zero resistance. There is a dramatic event that occurs, and it is quite rich with meaning. So that what happens is that electrons form into Cooper pairs. The force which holds them together in Cooper pairs is very, very weak. And so normally these Cooper pairs do not form at normal temperatures. But when you do form a Cooper pair, what you've done is taken two half-spin electrons, each of which is a fermion, and combined them into a single object, this Cooper pair, which is a spin 0 and hence a boson. And remember that while fermions obey the Pauli exclusion principle, bosons do not. And so you have this probability of electrons being on top of one another, or at least Cooper pairs being on top of one another. This is again repeating that normally they don't stay together, but if you get it sufficiently cold, then the Cooper pairs will form and stay. But that is not superconductivity just because you formed the Cooper pairs. You need to take these bosons, these Cooper pairs, and cool them still more until those bosons form into a Bose-Einstein condensate. And that is when you have superconductivity. So we need to talk more about Bose-Einstein condensates. This dramatic moment when, pow, in one step, the resistance goes to 0. So, if you take bosons and you cool them sufficiently, they all come to be in the same quantum state, and their probability, as they slow down, as their momentum gets closer and closer to 0, the probability distributions, that is their location, goes way up in its uncertainty, obeying Heisenberg, and those probability distributions begin to overlap one another. And when that happens, you have two objects which you can't tell which one of them it is. You can't tell where it is. And when you have two objects that you cannot distinguish from one another, the quantum reality is they are no longer two objects. That what you have is sort of an entangled single thing. They become one object. And in terms of superfluidity, which is a case of a liquid that flows with 0 friction, that if you were to take a coffee cup with superfluid in it and give it a stir, it would keep going around forever. as long as it was cool enough to be a superfluid. No friction to the motion. Well, alternatively, what about if you thought about that fluid as one big object? Rather than an atom going from one place to another, the atom is already at both places. We also will see an example of a superfluid flowing through holes that are too small for the atoms to fit through. But of course, as a quantum state, if its probability distribution goes to the other side of the hole, then it's already on the other side of the hole. And so you will see this fluid going through these two small holes. Superconductivity is very much, I think, a superfluid event, except it's being done with these Cooper pairs, that you have a current, that is electrons, moving without resistance, which is just like the friction here. And I think you could alternatively think about it as the electron is already at both ends of the wire. And so it is without effort that it goes from A to B because it's already at A and B. It's one giant object filling the whole wire. Well, let's look at these videos.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particularly is happening. Well, this is really one of the great phenomena in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them.
Okay, and now this one, and you will hear they talked about, well, here you will hear them talking about wave-particle properties overlapping. Even the very profound physicist at the end talks about wave properties, but really they are particles, but because of this probability distribution getting very large, to our consciousness that is more wave-like, but it's really an overlapping of the probability distributions he's talking about when he draws his little squiggles on the board.
In the 1920s, quantum theory was emerging as the best hope of understanding these strange phenomena. Its central idea was that atoms do not always behave like individual particles. Sometimes they merge together and behave like waves. They can also be particles and waves at the same time. Even for great minds like Albert Einstein, this strange paradox was hard to accept. In 1925, a young Indian physicist, Satyendra Bose, sent Einstein a paper he'd been unable to publish. Bose had attempted to apply the mathematics of how light particles behave to whole atoms. Einstein realized the importance of this concept and did some further calculations. He predicted that on reaching extremely low temperatures, just a hair above absolute zero, it might be possible to produce a new state of matter that followed quantum rules. It would not be a solid or liquid or gas. It was given a name almost as strange as its properties: a Bose-Einstein condensate. For the next 70 years, people could only dream about making such a condensate, which has never been seen in nature.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. They undergo an identity crisis. So let me show you what I mean by an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us, but in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. It's really difficult for me to explain just why that is, but that's the way it is. Now, as you go to very low temperatures, the size of these packets gets longer and longer and longer, and then suddenly, if you get them cold enough, they start overlapping, and when they overlap, the system behaves not like individual particles, but particles which have lost their identity. They all think they're everywhere. This little wave packet over here can't tell whether it's this one or that one or that one or that one or that one. It's there and it's there and it's there. They're all in one great big quantum state. They're all overlapping. They're all doing the same thing. And what they're doing, to a good approximation, is they're simply sitting at rest. This Bose-Einstein condensate is very difficult to imagine or to visualize. I can imagine what it's like to be an atom running around gaily, freely, bouncing into things, sometimes going fast, sometimes going slow. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system. There's nothing else like that in physics, and certainly not in human experience. So just to think about this causes me wonder and confusion.
Okay, me too. All right, the last topic is the Meissner effect, and typically when you study superconductivity, you will see this image of a magnet levitating above a disk, and naively we could say that, well, and it's important that this disk is cooled so that it becomes a superconductor, that this magnet, as it falls towards the disk, causes changing magnetic flux through the disk, which induces an EMF and hence a current, and this being a superconductor, that current flows perfectly, and that creates a magnetic field which holds this magnet up and levitates it. That's probably not far from the mark, but it was impressed upon me that in fact what the Meissner effect is not that the flux through this disk induces an EMF, but in fact when the disk is a superconductor, all magnetic fields are expelled, excluded, denied entry into this disk, and that somehow this region being without any magnetic field is what's going on to make this thing levitate. That doesn't make terribly much sense to me, so I'm just cautioning you. If it doesn't make sense to you, then we're together. Thank you for watching.